system at the top right panel. And then there are so many stars in our universe, and all those stars actually group together to form galaxy. For example, we live in a galaxy called the Milky Way, and you can see a picture, an artistic picture of our galaxy, that is the Milky Way, at the bottom left panel. And you can see the location of our solar system. It is not at the center of the galaxy, but it is at the outer skirts of a galaxy. So our galaxy, or at least visible galaxy, looks like more like a disk shape. And there are billions of such galaxies, spiral galaxies, elliptical galaxies, and irregular galaxies, and all of them together form our universe. But then there is another object in between that is called cluster of galaxies. So sometimes like hundreds of galaxies clumped together form a gravitationally bound object called the cluster of galaxies. And this is the biggest gravitationally bound objects in our universe, that is the cluster of galaxies. And you can see a picture of a cluster of galaxy at the right bottom panel. All these yellow objects are galaxies, right? So those galaxies are have come together to form a galaxy. And if we look at our universe from a broader perspective, this is how it looks like. So see this picture, it is our universe at large scale. If you observe your universe at large scales, so each point in this picture is a galaxy, and you see the galaxies are distributed in such a way that it looks like a web. So we know a web. So these galaxies are aligned in lines sometimes, and there are dark regions in this map. So those are basically empty regions, and there is not much material in that region. But this all these yellow particles are one galaxies. Now you can imagine. So we are living in a planet, and then planets and stars form solar system or other solar system, and those solar system together form galaxies, and that one big galaxy is basically a particle. So you can imagine how big our universe basically, or basically the visible universe. In principle, our universe is infinite. There is no boundary in our universe. But the visible universe, the universe that we can see using our eye or using a big telescope, that looks at large scale something like that. And this, you see this very bright yellow regions. There are so many galaxies are one place. Okay, so there is a nice video that demonstrates from small objects like planets up to the large scale structure universe. And then so I would like you to see that video, and you will understand the present how our present universe looks like more clearly. So let me show that video first, and then I will move on to the next topic. So let me stop this slide sharing, and then I will share the video. So can everybody see the video? I haven't started yet, but you can see the window, right?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir. Yes, sir.
Okay, so let me start it.
Yes, sir.
Okay, so I have stopped sharing it. There is not much that is interesting here. So could you hear the sound of that video?
Yes, sir.
Yes, sir.
Yes, sir. Yeah, that's great.
Yes, sir. Yes, sir.
Okay, so let me share my slide again. Right. So now we have some idea like how big our universe and how tiny we are in terms of the vastness of the universe. And so there is nothing to be proud of. We are very insignificant in the whole space-time. Let's move on to the next topic, that so we now have idea about our present universe. Now the question is the universe same also like the same in the past, or it was completely different? So the answer of that question is at this moment that universe was completely different in the past. It is not the same. So universe is not static, it's changing with time. And so let's discuss our beginning, how universe began, and then what are the major events that took place from the beginning to the present universe. So you see this picture. So universe started with a Big Bang. Big Bang is basically the starting point of our universe. Now, what exactly happened during the Big Bang, we don't know for sure. There are many ideas, many theories, but there is nothing that is very robust. Okay, so let's assume that universe started with a Big Bang, and initially it was full of radiation only. Radiation means electromagnetic radiation, that is light. There were no atoms or electron, protons like that we see at present. It was completely full of radiation, and then universe is also expanding. It is expanding, so it's the distance between two particles are increasing. And then as it is expanding, expansion is a adiabatic kind of expansion, so universe temperature is also going down. So initially universe was huge, highly dense, and the temperature was extremely high. But as it expanded, its temperature came down slowly, and then there's a period called the inflation when universe expanded extremely rapidly. And that inflation period took place when the age of the universe was 10 to the power minus 43 seconds to 10 to the power minus 35 seconds. So it's not even a second. Within a very small fraction of second, universe expanded hugely. And that episode was called inflation epoch. So inflation, you know the meaning of that word, inflation. So it's a rapid expansion within a very short time. And then it was believed that first particles, the basic particle, quarks and then leptons were formed. And then so initially there are also gluons also were there. So we know that the quarks are the basic building block of any elements. Quarks and then electrons, these are the elementary particles. You cannot break them further. And then some quarks combined together and formed protons, neutrons like particles. So we know that protons, neutrons, electrons are the elementary particle inside an atom. But initially there was no atom. These particles were basically free and were scattering with each other. But then but now universe is expanding and its temperature is going down. So at some point the temperature and density was such that proton and electron formed, they combined, and formed hydrogen atom and helium atom. So we know that in one hydrogen atom you have one proton and one electron, and then in helium atom we have two neutrons, two protons, and two electrons. So basically one electron and one proton combine to form hydrogen atom, neutral hydrogen atom, and then two protons, two neutrons, and two electrons combine to form helium atom, right? So so that time it was the first time that atoms were formed in the form of helium and hydrogen. But the higher there are higher atomic mass atoms also, right? We have helium, hydrogen, helium, and then lithium. There are more than 100 elements in the periodic table, but at the very initial phase of the evolution, only 2 or 3 kinds of elements were formed, like hydrogen, helium, and some lithium, not beyond that. So our early universe was full of hydrogen and helium, and some very small amount of lithium. And that during that time, so one proton and one electron combined and formed neutral atoms. And then you have also photons, that's electromagnetic radiation. They were scattering with this electron and proton. But now, since electron and proton were combined and they became neutral, charge neutral, photons were no longer scattering with them. They became basically free. So they started to move in the space freely. There's nothing that can stop those photons. So those photons became relic radiation, and that relic radiation still exists today. And that radiation is named cosmic microwave background radiation. So we can still measure that radiation from that very early universe. And that was the first proof that universe actually had a hot phase, hot Big Bang phase. And that was the first major evidence that our universe started with a Big Bang. Before the discovery of the cosmic microwave background radiation, there are other theories also, like steady state theory, quasi steady state theory, where universe basically was kind of static, not evolving with time. But because of this discovery of cosmic microwave background, those theories are ruled out because those theories cannot predict cosmic microwave background radiation. So that episode is called cosmic recombination. So recombination means it's a combination between electron and proton, and that episode is called cosmic recombination episode. So that was the first few 100,000 years. Within the first few 100,000 years, everything, all these important things happened. So like synthesis of nucleons, formation of atoms, and formation of radiation, cosmic microwave background radiation. So all these important things happen within a very short time of the evolution of the universe. And after this recombination, as I said, we have this neutral hydrogen atom and neutral helium atom. So the universe was full of hydrogen and helium initially, and some lithium. And and there are no stars, galaxies like that. So you have just seen that the universe is full of stars, galaxies at present. But those objects were not there at the beginning. They formed much later. Okay. So let me show you the next slide, where actually what happened after the recombination. So in this picture, it's the same picture. It is showing the evolution of universe. So x-axis is the time axis, and the right side is the present universe. Left side is the initial universe, the Big Bang, and after events after that. And you see the major events that took place while during the evolution of the universe. So the Big Bang, and then we have discussed all these episodes like nuclear synthesis, atom formation, and recombination. So after the atomic neutral atoms like hydrogen and helium were formed, a universe entered into an age called the Dark Age. You see this, I'm indicating that episode with my cursor. That is called the Dark Age. Why it is dark? Because there were no sources of light. So what makes universe visible? Because light from stars makes universe visible. But there are no stars and galaxies during that time. So universe was completely dark. And that's why that episode is called the Dark Age. And Dark Age was actually very long and elongated episode. So universe went through a long and long dark phase. It was completely dark. And that episode is called the Dark Age, and it was full of hydrogen and helium. And it is believed that when universe was like 0.1 billion year old from the Big Bang, first stars, the stars that we see, the first stars were started to form during at the end of the dark ages. Initially, there are only few stars formed, and later more and more stars were formed. And once stars were formed, you know the light from stars that actually made the universe visible. So this onset of the first stars are this episode is called the cosmic dawn. So we know that the dawn of a day is the time when our day starts, like from the dark night, our earth becomes visible, or it becomes when the just during the dawn. So using the same analogy, we have similar situation in the evolution of the universe. So during the cosmic dawn, universe became visible. So that's it. And then those stars, as we know that stars emit light, and some of the lights are very high energetic light, like with energy of 1 photon greater than 13.6. Now, what is 13.6 electron volt? Why it is important? Because we know if we have a 13.6 electron volt photon, that can ionize a hydrogen atom, because hydrogen atom needs only 13.6 electron volt photon to make it ionize. So light of energy 13.6 electron volt from stars again started to ionize the hydrogen atoms. So hydrogen atoms were neutral before that, but stars, light from stars actually started to ionize those hydrogen again. So they were ionized before during the Big Bang or just after the Big Bang, but then they became neutral, but again they are becoming ionized because of the light from the stars. Now those stars actually started to ionizing their surrounding regions, and those regions started to grow because stars are continuously emitting ionizing photons. So those regions will grow in space, and those are like ionized bubbles. So those are like ionized bubbles inside neutral hydrogen medium. But later they grow and grew, and then two nearby ionized regions started to overlap with each other, and then the entire universe became almost ionized. So this episode, just after the cosmic dawn, the ionization of hydrogen that took place, and that was also an extended process. And during that time, ionization of hydrogen took place, and it is called the epoch of reionization. That was another big event in the evolution of our universe. And so this is, as you can understand, this cosmic dawn and epoch of reionization is basically one of the major events in the universe. Unfortunately, we know very little about this epoch, and recently there have been huge developments actually in terms of observing this epoch. So scientists from all over the globe actually trying to understand what happened exactly during that time, and people are they have built a radio telescope, because radio telescope is the only promising way to observe this epoch. You cannot observe this epoch just by optical telescope. There are many challenges for it. So radio telescope is one of the promising tools to study this epoch, and I'll talk about that later. So now the hydrogen became ionized, and all these galaxies and stars started to form, and universe started to become it started to look like the present universe. So galaxies were formed, right? And then another big event, significant event actually happened after that. That was the dark energy dominated universe. And that was the time when universe was only 6 billion years or 6 to 7 billion years old. During that time, dark energy started to becoming dominant over the normal energy, like dark matter or baryonic matter, visible matter. So what is important about the dark energy? Dark energy is some kind of very elusive force that actually tries to push. It has repulsive force in nature. So if you have two galaxies with the distance of r, then there will be gravitational force between two galaxies, and we know how to calculate the force. That is g mm by r square, where m is the mass of the galaxy. and this r is the distance between two galaxies. So that is the attracting force. So since they have attracting force, they will come close to each other with time. So that force we know about, gravitational force, and Newton actually has told about it. But if there is a dark energy and if it is dominating over the gravitational force, instead of coming to each other, they will actually move away from each other, and that was something very unexpected. So we know nothing about dark energy. Only thing that we know about is it is repulsive in nature. So if there is a dark energy, instead of coming to each other, they will actually move away from each other. And at present, if you consider the total energy of our universe is 100%, that is the mass and energy, which is equivalent. If you believe Einstein theory, then if you assume it to be 100, 70% is actually consists of dark energy. So it's a huge percentage dark energy, and present universe is actually, because of this dark energy, present universe is accelerating universe. What does that mean? That means that two particles are actually moving away from each other. So basically there is a velocity between two particles, but that velocity is changing. It is increasing with time. Let's say velocity between two particles at this moment is 200 km per second. But if you measure the velocity between two particles, let's say 10 years from now or 1 billion years from now, velocity would be 400 km per second. So velocity between two particles are increasing with time. And that is something not known. So no known theory can explain this. So that's why this dark energy, idea of dark energy came in. And so what is that? What is the nature of dark energy? What is the microscopic reason for that? We don't know. So this is one of the biggest mystery in the current universe. And scientists are actually trying hard to understand that. Okay. So that was about the evolution of universe. So if you just consider what is our universe, current universe is made of, you see this right panel pie chart. So this 72%, as I said 70%, so it is 72% is made of dark energy at present. Okay, so I'm stressing the word at present. At present it is 70%, 72% is dark energy, 23% is dark matter, and remaining very small part is 4.1%, 4.6% is essentially baryonic matter. So this 4.6% is the only component that we know of. So this is the component. It is made of the known particles like electron, proton, quarks, photons, all these known thing, and the theory of that we understand. Those particles actually consist of only 4%. So more than 95% is actually unknown, and among them 72% is dark energy and 23% is only dark matter. So you now understand that most of the universe is unknown to us. We don't know what is dark energy, we don't know what is dark matter. These are the two biggest mystery in the modern cosmology. So dark matter, I will come to that a bit more. So dark matter and dark energy, these are the two biggest mystery, and people are actually really trying hard to understand what those are, right? And as of now, as of today, we don't know what they are. But if you look at the past universe, and if you calculate the same energy budget, you see in the past universe there was no dark energy. So dark energy is actually dominant at present. There is nothing called dark energy at the past. So 63% in the past was dark matter, 10% was in the form of neutrino, 15% is photons. So as I said, early universe was full of radiation. So radiation means photons, right? So 15% significant amount was photon. But at present you don't see photons. So photons are very insignificant at present. But in the early universe it was very dominant. At present you have dark energy dominated, but in the early phase it was insignificant. So universe is evolving, and the known matter, that is atoms, the basic building block of any material, is only 12% in the past. So known matter essentially consists of very insignificant. Okay, so now move on to the next topic, that is dark matter. So what is dark matter? So let me explain an experiment from where the idea of dark matter came in. So actually, if you look at the galaxy, a spiral galaxy, in spiral galaxy, stars are moving around the center of the galaxy, and they have some rotational velocity. So that rotational velocity, if you plot, so this is the plot I am showing is the experimental results. If you plot the velocity of stars as a function of the distance from the center, so x-axis is the distance from the center, and y-axis is rotational velocity. So if you plot it, you see the green line. So the rotational velocity is kind of increasing, and then it's slowly increasing with radius. However, if you only consider the visible matter, and if you apply the Newton's theory, the expected velocity should be this bottom line, this orange line, dashed orange line, right? Now you see the discrepancy. From the dashed orange line, you expect the velocity to decrease with radius, but what you observationally see, it is increasing, and so this is some discrepancy. We cannot explain the observed fact with our known theory. Then people came with an idea of dark matter. So this bottom line was calculated assuming only the visible matter. So if you have visible matter, your velocity should be like this. But then people have assume that so if you cannot explain, then let's assume some invisible matter, dark matter, which we cannot see, but it is there. So that is why this idea of dark matter came in. So it has gravitational force, but you cannot see them. So if you assume that kind of idea, then you can explain your dark matter. But then if you so now see, the dark matter is something that has gravitational force, that is attracting, but you cannot see it. Now so far we don't know what is dark matter. So what it is made of, like from the baryonic matter, we know it is made of proton, electron, quark, gluons, and all these things. We know exactly the behavior and properties. But for dark matter, we don't know what they are made of. Like whether they are made of particles or whether they are made of some exotic things, we don't know a lot about it. So this is another mystery. And this scientist, Vera Rubin, she has actually studied the behavior of dark matter extensively. And because of her research, the idea of dark matter is now established theory. It is an established fact. Now it is up to the theorists to explain the dark matter. Okay, now another important aspect of our universe is that stars, right? So stars are basically the source of light, the major source of light in our universe. And stars, as I said, started to form when universe was like 0.1 billion years old. And because stars are there, we are here. It supplies all the energy we need. For example, in our Earth, sun supplies all the energy that we need. So stars are very important in the study of our universe. So let's start understand the life cycle of a star, how stars are born, how they live, and how they die. This is another important questions that we all want to know. So the life cycle of a stars is very interesting topic, and so I will show you a video after discussing this topic. So basically, stars are the source of light. Now, how these lights are produced inside the star? So stars, as I said, that initially our universe was full of hydrogen and helium. So those hydrogen and helium clouds, actually they started to sink because of the gravity. They started to sink. Okay, initially you have a broader extended cloud of hydrogen, but because of the gravity, those broader and extended cloud actually started to sink. Now once you sink a object, its temperature will rise. Why? Because see, let's say you have a particle at the height of h from the ground. So its potential energy would be mgh, mass into gravitational acceleration into h. H is the height from the ground, so that is potential energy. Now if you just leave that particle, it will go down and its height will be reduced, and when it touches the ground, height will be 0. So potential energy will be 0.
Yes, sir. You're audible.
Yes, sir.
Yes, sir. Yes.
Yes,
Yes,
sir,
sir.
you could do, sir.
Hello, sir. Sir, is this over or? Okay, okay, sir. Okay, sir.
ক্লাস কি শেষ হয়ে গেল না হচ্ছে?
my microphone off. Yeah. Okay. Sorry for the interruption. Actually, my network got disrupted. So I'm just trying to give this talk using my mobile. So it is bit a slow network. So can you hear me properly now? So then I can. Okay.
Yes, sir. Yes, sir.
Okay. So let me share my slide once again. So you can see my slide.
Yes, yes. Yes, sir.
Okay. So we were at this slide, I guess. Yes. So as I was explaining to you that those hydrogen clouds started to sink, and then at some point temperature reached to a point that hydrogen atoms started to fuse with each other. And when two hydrogen atoms fuse fuse each other, then it will form helium. And while during this helium fusion process, you have enormous amount of radiation that is coming out because of this reaction. So hydrogen actually combine to form helium, and during this process you have photons coming out, and those photons are the sources of energy inside a star. So that happens at the core of a star, and that phase is actually called star. So what is stars? Basically, it's a fusion between two hydrogen atoms, and then emission of radiation. Now, once this radiation started to they started to escape from that center of that cloud, and gravity actually is trying to pull things at the center. So this is a two force, one gravity force and one is radiation pressure, which is outward. They are opposite in nature, and these two forces tries to balance each other, and it becomes a stable object, which we call as star. And that particular phase, when hydrogen is burning, it is called the main sequence stars. So this is the star we are aware of. Now see, hydrogen are continuously getting fused. So at some point hydrogen will be completely burnt out, because you have finite amount of hydrogen at the core. Once that happens, this fusion process will stop, and there will be no radiation coming out. So there will be no force that will oppose the gravity, right? So in that phase, this core will start collapsing further, and outer layer of that star, that cloud, will expand because of this radiation. And that, because of that expansion, as I said, expansion makes things cooler. So the outer shell will be cooler and cooler, and it will look red. And that part you can see, it is called red giant phase. This red giant phase, and it will expanded so much that, for example, if our sun reaches to this red giant phase, this red giant envelope of that star or sun will actually eat up Mercury, Venus, and it will reach up to the point of Earth. So we will also be inside the red giant. And the core that was actually stopped burning hydrogen, it can the future of that core will have two possibilities. One, if the mass is very small, like our sun, it will become a white dwarf. So basically the core will collapse further, and then electron degeneracy pressure will start to kick in, and that will somehow stop the further collapse of that core, and that is called white dwarf. And after a long time it will become a black dwarf. It will not emit anymore, it will become a black dwarf. But if the mass of the core is more than 1.4 times of the solar mass, that is called Chandrasekhar limit. Actually, it was the Chandrasekhar who actually gave this theory. If it is more than 1.4 times, then this electron degeneracy pressure will not be able to stop the collapse, because it is collapsing. So that force is not enough to stop the collapse. because mass is so much that gravitational force will actually beat the electron degeneracy pressure, and as a result electron and proton combine and will form neutron. So it will be a fusion process, it will become a neutron. So the entire star will convert into a neutron star. So electron protons are converted into neutrons, and there are also neutrons from the beginning. So everything will be converted into neutrons, it will become a neutron star. And so it is very compact and only made of neutron star. So it is so compact that if you take one matchbox size of neutron star material, weight of that would be 1 cube kilometer of earth size material. So 1 cube kilometer of earth size material, you can imagine. So 1 kilometer, 1 kilometer, and 1 kilometer cube of earth size material, the weight is extremely high, and that weight is very equal to the weight of one matchbox size of neutron star. So you can imagine how compact and dense and material neutron star is. But if the mass is even more, let's say 10 times of solar mass, the core mass is 10 times of solar mass, then actually even neutron degeneracy pressure is not enough to oppose the collapse. So higher the mass, more the internal gravitational pressure, gravitational force. So if the mass is more than 10 times of solar mass, it will beat the neutron degeneracy pressure, then it will become a black hole, right? So there are two possibilities, one is neutron star and another is black hole. So black hole is something, let me explain it a bit more. What is black hole? So black hole is a space, is a place in a space where gravity pulls so much that even light cannot escape from that region. So we know the escape velocity from an object is basically 2 gm by r, right? 2 gm by r. Now g is constant. M, if you increase the m and reduce the r, escape velocity will be more than c square at some point. So if you increase the mass and if you make it compact, that means r is small, it will become a black hole. Black hole means the escape velocity will be more than c. So even light cannot escape. So there is nothing that can have velocity more than light. So nothing can escape. So that's why it's a black hole. So black hole is something, nothing can escape from that black hole. Now there are various types of black holes. One is stellar black hole, and we just have discussed how it is formed. It is the end product of a star. If the star is very massive, it will eventually become a black hole. But then there are other types of black holes like supermassive black hole, which are formed at the center of a galaxy. So those are formed, actually there is this idea that these small black holes will accrete matter from the surrounding regions, and it will actually co-evolve with the galaxy, and mass will be extremely high. So these are supermassive black holes. Now it is extremely difficult to actually image black hole, because as you see, nothing is escaping from black hole, so we cannot see it, the black hole. What I can do, we can image the surrounding regions. So if there is a black hole, it will start accreting the material from the outside. Now those material can sometimes emit light, like X-ray radiation and other radiation, and those parties you can image. But the problem is that region is extremely small, and those black holes are very far. It's not just like a very close by. So they are very far. So their angular size in the sky is extremely small. So angular size is calculated by the dimension of the black hole by the distance. So distance is so much that angular size will be some microseconds, and it is very difficult to observe with those objects given the current telescopes. But recently in 2009 there was a success. They used Event Horizon Telescope to image the black hole, and you see this first image of black hole. Actually, it is not the image of black hole. The center black region is the place where the black hole is there, and the surrounding light is essentially the image of that surrounding materials which are coming. But this is the first time now people have convincingly proved that there is a black hole, and you can image that, particularly the image of the surrounding regions. Now it is an exciting topic for modern cosmology to image the black hole and understand its property and various other things. Right. Now, moving on to the next topic, I talked about neutron star. It is made of only neutron star, but neutron star itself is not very interesting because it is very difficult to detect. But if it is rotating, if neutron star rotating, some neutrons are rotating very fast, 100 times or 1000 times per second, right? So our Earth is rotating once in 24 hours, but these objects, these neutron stars, they can rotate 1000 times per second. You can imagine how fast they are rotating. Now, these neutron stars are sometimes they are emitting at the like a jet from the two sides. You can see this image. They are emitting from two sides, and it is rotating. So these two sides are rotating. When one beam of light passes through the Earth, you can see it, and when it goes off, you cannot see it. So it's like a pulsar. So pulsar names comes from the fact that you can see pulse like signal. So when it is towards you, you see light. When it is away from you, you don't see. So that's why it is pulse, and it is millisecond period. So like in 1 second, you have 100 such pulses. So it's a very highly magnetized objects, very dense objects, and as I said, it's very compact, and so you can observe those neutron stars by observing pulsars. And these two scientists actually first discovered pulsars in 1967, Jocelyn Bell Burnell and Anthony Hewish, and they both actually this discovery was awarded Nobel Prize in physics for in 1974. So important was that discovery, right? Now, so all these things I have discussed. Subhati, how much time I have? Okay, thank you. Actually, I have already spent 1 hour. Yeah, sorry for the delay. So let me finish it quickly. The next topic that I would like to discuss.
Hello, sir.
Yes.
Sir, there is a new telescope that James Webb. Sir, can you please talk it about on that James Webb?
Okay, so okay, I'll talk about it at the end, very end. Okay.
Okay.
So wait, okay, for a few minutes, and then I will say some brief information about that. Okay, so now let's so far I have discussed all the major important topics that people are concerned about at present. Now, how to observe our universe? Now, there are many ways to observe our universe. We know that actually we can observe our universe using telescope, and mostly by optical telescope. But optical telescope is a small part of the electromagnetic wave that is used. There are other part in the electromagnetic wave like radio wave that is not in optical band. You have infrared, you have X-ray, you have gamma ray, and you can actually observe our universe using that radiation also. So one of the important radio telescopes is radio telescope. It actually detects the radio part of the electromagnetic wave. Yeah. So why radio telescope is so interesting? Because radio telescope and optical telescopes are the two kinds of telescope that can be built and set up at the ground, at the Earth's surface. Because optical light and radio lights are the only two parts of the electromagnetic radiation that can penetrate through our atmosphere. No other radiation like gamma ray, X-ray, infrared, microwave, they cannot penetrate through our atmosphere. So if they cannot penetrate, you cannot actually observe it. So radio and optical, those are the two telescopes regime that you can observe from the Earth. So that's why it is important. Now, when you build a telescope, you have to actually keep two things in mind. One is the resolution of the telescope, and another is the sensitivity. What is the resolution? It's basically how I guess how closely separated objects you can distinguish. Let's say you have a bad telescope, then these two objects we are very close by, they will appear one object. But if you have very good telescope, high resolution telescope, you can separate them out. So that is called the resolution. And sensitivity is the quantity that is basically how faint object you can observe. Like let's say from our naked eye we can observe sun, moon, and some other objects, right? Not fainter objects. But if you have a telescope with bigger telescope, you can observe much fainter objects like supernova and all these things. So you need you need to have a higher resolution and a higher sensitivity. And if you increase this, if you want to have better telescope, the size of the telescope should be very high. So that's why people are actually started to building big telescopes, like the telescope we see this right bottom panel. This is the this is what this China actually has built recently, 500-meter telescope. Just imagine 500 meter. Normally one football ground is 100 meter, 200, 150 meter. So 4-5 football ground in one line can fit in this telescope. It is so big. So it is built between mountains, so valley in the mountain. So it's a very big telescope, and big telescope means it will have bigger resolution and bigger higher sensitivity. In India, we have many such radio telescope like GMRT. GMRT was once world's biggest radio telescopes. You see some pictures of GMRT. It was built by Professor Govind Swarup, and it is still there, and it is very important radio telescope. That is only thing that that is world class in the research of astronomy in India. So it's we are very proud of that, and people all around the globe actually use this telescope to observe various astrophysical objects. And Professor Swarup was actually pioneer of radio astronomy in India. He just passed away last year. He was 90 years old. So I have met Professor Swarup many times, and very energetic person. So you see the broader view of the GMRT. It is near Pune. So if you have opportunity to go there, so please visit this site. It's a wonderful telescope and sites. Then the next big telescope that is coming up is the Square Kilometer Array. The Square Kilometer Array will be the world's biggest radio telescope, and it has two parts. One is SKA mid. SKA is Square Kilometer Array, and SK low is the SK low. It will be built in Australia, and SK mid will be built in South Africa. Basically, two single telescope, but it is so big that it is now spread in 2 different continents. And these are some of the parameters. Let's skip that. And basically the point is that it is an international telescope. It is not actually built by one country, but in many countries, including India. So that is an important part. India is one of the member countries of this Square Kilometer Array. And in India, we have SKA India Consortium. And there are many universities and institutes are part of that, and including Presidency University. So just to compare how big it is, it has actually 135 times more survey speed than the current base telescope, and then the sensitivity is 5 to 8 times more than the base telescope available at present. So you see, it's a very big telescope, very useful telescope. And what are the science goals? The science goals are basically, there are many science goals, but let me highlight few. That it can observe pulsars in such a precedented manner that it can be used to actually prove or disprove Einstein's theory. So Einstein's theory has been proved so far using weak gravitational field limit. It has not been proved in strong gravitational field limit. So SK will be able to actually prove or disprove Einstein's theory in strong gravitational field. And then it can also shed light on the dark energy dark matter that I have talked about. And then it can also give you idea, like if we are alone in the universe, like only Earth has life, human lives, or is there other planets where life can form, right? So basically it will look for organic molecules. That is the basic building block of life. So it can actually, if there is organic molecules out there, SK will be able to find them. And also it can image thermal emission. from the dust. In the habitable zone. So if there is habitable zone means it's an environment where life can sustain. So and there are certain properties, so SK will be able to image those regions. And of course, the important episodes in the universe, that is cosmic dawn and epoch of ionization, that can also be studied using the SKA, right? So it is another science goal for the SKA. So I'd like to stop here, and then if you have any question, I can try to answer. Thank you for your attention.
Sir, yes, sir. Sir, is there any place where light cannot sustain?
Sorry, I could not hear you.
Sir, is there any place that could not sustain?
Is there any place where life could not sustain?
Yes, could not escape.
Okay, so see, if I understand your question correctly, life. In order to life to sustain, you need many favorable environment, right? Like you need oxygen, you need water.
No, sir. Not light, LIGHT.
Oh, light. Okay. So your question is there any place where life cannot
Escape?
Oh, okay. So black hole is the one such object, right? So light, if you are inside the black hole, light cannot escape from black hole. Yeah.
Okay, sir.
And regarding your question of James Webb Space Telescope, so James Webb Space Telescope is basically it's a kind of it's an optical and infrared telescope, and it is being built mainly by US, but some other European countries are also involved. And it is a space-based satellite. So it will not observe from the Earth's surface, but it will be sent outside the out to the space, and it will have a 10-meter diameter of telescope size. So it can actually observe the faintest objects in the sky that has not been observed yet. Because of the, as I said, that you need bigger telescope to actually observe faint objects and small objects. Now, so far, Hubble Space Telescope was the only important telescope working in the optical and infrared, and that has only 2-meter diameter. So now, if you have a 10-meter diameter telescope, it will have bigger sensitivity, it will have bigger resolution, so it can observe faint objects. So faint objects basically are the objects which are very far. Right, so if you put things very far, it will appear faint. So it can observe faint objects. That means it can observe the objects which are formed during cosmic dawn, during epoch of reionization, right? And then you can actually observe the cosmic dawn using James Webb Space Telescope. So there are many unanswered questions can be answered, and so yeah.
Okay, sir. Thank you, sir. Sir, but why 10 meters? Sir, we can do 100 meters, so we can see.
So now see, if you want to make, of course, if you can do it, it is better. But let's say you want to send 100-meter optical telescope to the space. How big is your rocket? Like by right, you have to send by some rocket, right? Now you want to send 100-meter things using a rocket. Is it practical? It is not practical. It is difficult. So we have to consider practical aspects also. And also it is not about sending it to the space. 100-meter mirror, building a 100-meter mirror is also difficult. It has to be so accurate. The plane of the mirror, that is 10. So far 10 meter, 20 meter is possible. It is not possible beyond that.
Okay, sir. Thank you, sir.
Yeah. Any further question? Could you follow what I have discussed or it was bit difficult to follow? That's why I want to hear from you.
No, sir, it is very good.
Hello, sir. Oh, this big size telescope where in Pune?
So it is near Narayangaon. It is about 2.5 hour bus journey from Pune. It is in Narayangaon.
Okay, Narayangaon, right?
Yeah.
We
Are
can
you
travel without pass, na? Any special pass or
No.
required for-
Actually, no. It is not open for everyone. So if you want to go there, you have to go to their host institute that is in Pune. That is called National Center for Radio Astrophysics, right? So if you
Okay, how to
if you
get
visit,
this?
no, so if you go there and ask that you want to visit Pune, they will give you pass. So they encourage students to visit
in
that
where?
site.
Which institute?
Sorry.
Okay. Can you help any
No, so
number?
normally if you visit there in groups,
Or
they are
how to
actually no, you can see, you can visit NCRA and then you can request them that you want to visit, you are students from engineering background and you want to visit GMRT. They will give you permission and you can just go there. Even they have buses from there that is leaving Pune every morning at 6 or 6:30 p.m. AM. You can avail that bus as well if they have a seat, and they will take you to that site, and then that bus returns Pune in the evening, so you can come by that bus.
Okay.
You can roam
For
around.
that, any online process are here?
I don't think there is online process. You can go to the site. So are you in Pune now?
Yeah.
Okay, so you
Yes,
can
sir.
go
Yes,
to you know this Pune University campus.
Okay, Pune University campus. I know.
Yeah, so it is inside that university campus. So if you
Okay.
if you go to Pune University and ask anyone that where is this National Center for Radio Astrophysics, everyone knows that. So if you go there and if you actually ask someone, like if you can go to the office of that center and ask that you are students from engineering background, you are interested to actually visit GMRT site, they will ask, they will actually help you.
Okay, sir.
And if you go there in a group, they will even book a bus for you free of cost.
Okay.
Right?
Thank you, sir.
Yeah, welcome. Yes. No, so if you if some like for some reason if you go there and then you can actually have one 1 and 2 days spare time, then you can go. It's a very nice quiet place. Yeah, I have been there several times. Yes, so normally if you yes, if you go there in a group like 10-15 students or even like 5-6 students, they arrange a demonstration like what is GMRT about and how does that work and how they collect data and how they make images. So they arrange for that because that is their job. Uh, Okay, so actually these many telescopes, many these telescopes, when they are connected using fiber optics and their signals are correlated, that is called interferometric mode of telescope operation, and that is required because you need higher resolution. Right. So for higher resolution, your diameter should be large. Now we cannot make one single telescope of, let's say, 1 kilometer diameter. That is impractical. So instead of doing one single telescope, you can make small telescope and put them 1 kilometer apart, and that gives you the same resolution like a single telescope. So this is more effective and less cost wise it is efficient, and yeah. So and also you need land, 1 kilometer continuous land, that is also not easy to get it around Pune. So that's why they have built this. Yes, so that has one advantage in some science cases, you need so for this single telescope, for example, this if you want to observe pulsar, pulsars are basically very compact objects, and and that has to be observed in some special mode called phased array mode. And so it is efficient. It is very efficient for single telescope to observe pulsar compared to the interferometric telescope, because if you combine all the signals, sometimes that is problematic to find pulsars in interferometric mode. Yeah, thank you.
No, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Tulasi.
Sir,
Thank
we
you, sir.
want one more. We want one more session for another topic. This is very interesting topic. Please arrange.
Okay,
Thank you, sir.
try. I shall try. Yeah, I shall try and see if I can give you one more talk. Thank you. Thank you for listening to me. Yes. Yeah. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.